Chapter 2 Number Systems, Operations, and Codes. Digital Fundamentals. Chapter 2 Number Systems, Operations, and Codes. Decimal Numbers. The decimal number system has 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The decimal numbering system has a base of 10 with each position weighted by a factor of 10. Binary numbers 2 digits called bits, 0 or 1. Rightmost bit is least significant bit. Leftmost bit is most significant bit. Each position is weighted by a factor of 2. 23, 22, 21, 20. 2 to 1, 2 to 2, 2 to 3, 2 to 4. Decimal point. Counting in binary decimal number. Binary number 0 0 0 0 0 1 0 0 0 1 2 0 0 1 0 3 0 0 1 1 4 0 1 0 0 5 0 1 0 1 6 0 1 1 0 7 0 1 1 1 8 1 0 0 0 9 1 0 0 1 10 1 0 1 0 11 1 0 1 1 12 1 1 0 0 13 1 1 0 1 14 1 1 1 0 15 1 1 1 1 23 22 21 20. Figure 2:1 Illustration of a simple binary counting application. Thomas L. Floyd Digital Fundamentals, 9e. Copyright 2006 by Pearson Education Incorporated, Upper Saddle River, New Jersey 07458. All rights reserved. Binary numbers. The binary number system has 2 digits, 0 and 1. The binary numbering system has a base of 2 with each position weighted by a factor of 2. Binary to decimal, add the weights of all the bits that are 1. Ignore the bits that are 0. Convert 1,101,101 to decimal. First determine the weights. 26, 25, 24, 23, 22, 21, 21, 101, 101. 1101, 101 equals 26 plus 25 plus 23 plus 22 plus 20. Equals 64 plus 32 plus 8 plus 4 plus 1 equals 109. Decimal to binary conversion. Sum of weights method. Repeated division by 2 method. Conversion of decimal fractions to binary. Repeated division by 2. Divide the number by 2 and write down the remainder. Continue the process until the whole number quotient is 0. Convert decimal 19 to binary. Convert decimal 45 to binary. Decimal fractions. Repeated multiplication by 2. Multiply the decimal fraction by 2. Write down a carry bit if more than 1. Continue process until you have the desired number of bits or when the fractional part is all zeros. Convert 0.3125 to binary. Carry MSB LSB 0.0101. 0.3125 by 2 equals 0.6250. 0.625 by 2 equals 1.251. 0.25 by 2 equals 0.500. 0.50 by 2 equals 1.001. Binary arithmetic. Binary addition. Binary subtraction. Binary multiplication. Binary division. Complements of binary numbers. 1's complements. 2's complements. Complements of binary numbers. 1's complement. Change all 1's to 0's and all 0's to 1's. Complements of binary numbers. 2's complement. Find 1's complement and then add 1. Sign numbers. Topics for signed numbers. Signed magnitude form. 1's and 2's complement form. Decimal value of signed numbers, how to convert. Range of values, max and min. Floating point numbers. Signed numbers signed magnitude form. The sign bit is the leftmost bit in a signed binary number. A 0 sign bit indicates a positive magnitude. A 1 sign bit indicates a negative magnitude. Signed numbers 1's complement form, 2's complement form. A negative value is the 1's complement of the corresponding positive value. 2's complement form. A negative value is the 2's complement of the corresponding positive value. Signed numbers decimal value of signed numbers sign magnitude. 1's complement. 2's complement. Signed numbers range of values total combinations equals 2n. 2's complement form. 2n, 1, to plus, 2n, 1 to 1. Range for 8-bit number, n equals 8, 28 to 1, equals minus 27 equals minus 128 minimum plus 28 to 1, 1 equals plus 27 to 1 equals plus 127 maximum. Total combination of numbers is 28 equals 256. Signed numbers. Range for 16-bit number, n equals 16, 216 to 1, equals minus 215 equals minus 32,768 minimum plus 216 to 1, 1 equals plus 215 equals plus 32,767 maximum total combinations is 216 equals 65,536. 64k. 8-bit examples. 10 million equals minus 128. 11,111,111 equals minus 1. 10,000,001 equals minus 127. 0,1111111 equals plus 127. Signed numbers floating point numbers 2 parts 3 forms. Can represent very large or very small numbers based on scientific notation. Binary point floats. 2 parts. Mantissa represents magnitude of number. Exponent represents number of places that binary point is to be moved. 3 forms. Single precision, 32 bits, float. Double precision, 64 bits, double. Extended precision, 80 bits, long double. Also have quadruple and quadruple extended, single precision IEEE 754 standard. 32 bits. S exponent, E, mantissa, fraction, F. 1 bit 8 bits 23 bits. IEEE 754 standard. Mantissa, F, has hidden bits so actually has 24 bits. Gives 7 significant figures. First bit in mantissa is always a 1. Exponent, E, is biased by 127 called excess 127 notation. Add 127 to exponent so easier to compare. Range of exponents is minus 126 to plus 128. Sign, S, bit tells whether number is negative or positive. Single precision. Example, convert 577,710 to floating point. First, convert to binary using divide by 2 method. 577,710 equals 10,110,100,100,100,012. Positive number, so sign bit, S, equals 0. Second, count number of places to move binary point. 10,110,100,100,100,012 equals 1.01101000100001 by 212. Add 127 to 12 equals 13,910 equals 100,010,112. 01 triple o 1 o double 1 o double 1 o 1 double o 1 triple o 1 triple o triple o triple o double o. SCF. Fill in with trailing zeros. Montessori's fractional part, 1 1 0 1 0 1 0 0 0 1. Finally, put everything together. Special cases 0 and infinity are special cases not a number, none. Can have plus 0 or minus 0 depending on sign bit. Can also have plus or dash. Not a number, none. If underflow or overflow. Type. Exponent. Montessori. Zeros. Denormalized numbers. Non-zero. Normalized numbers. 1 to 2e minus 2. Any. Infinities. 2e minus 1. Na, ands. Examples type exponent Montessori value 0 o triple o, double o double o. O double o, double 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 o double o. 0.0. 1. O triple 1, double 1, double 1. 1.0. Denormalized number. 1 double o, double o 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 double o. 5.9 times 10 to 39. Large normalized number. 1 triple 1, triple 1 0. 1 double 1, 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 double 1. 3.4 times 1038. Small normalized number. O triple o, triple o 1. 1.18 times 10 to 38. Infinity. 1 triple 1, double 1, double 1. None. O 1 no, double o double o, double o double o, double o double o, double o double o, double o double o. Double precision exponent is 11 bits, so uses excess 1023 notation. Montessori has 53 bits, 1 hidden. 53 bits give 16 significant figures. Arithmetic operations with signed numbers. Addition. Subtraction. Multiplication. Division. Arithmetic operations with signed numbers. Addition of signed numbers. The parts of an addition function are augend, the first number, addend, the second number, sum, the result. Numbers are always added 2 at a time. Arithmetic operations with signed numbers. 4 conditions for adding numbers. 1. Both numbers are positive. 2. A positive number that is larger than a negative number. 3. A negative number that is larger than a positive number. 4. Both numbers are negative. Arithmetic operations with signed numbers. Signs for addition. When both numbers are positive, the sum is positive. When the larger number is positive and the smaller is negative, the sum is positive. The carry is discarded. Arithmetic operations with signed numbers. Signs for addition. When the larger number is negative and the smaller is positive, the sum is negative. Choose complement form. When both numbers are negative, the sum is negative. Choose complement form. The carry bit is discarded. Examples: 8-bit numbers. Add 7 and 4, both positive. Add 15 and minus 6, positive greater than negative. Add 16 and minus 24, negative greater than positive. Add minus 5 and minus 9, both negative. oooooo1117 plus oooooo1000 plus 4000111111 oooooo111115 plus 11,111,010 plus minus 610001019. Discard carry. 16 plus 11,101,000 plus minus 24 11,111,000 minus 8. Sign bit is negative, so negative number in 2's complement form. 11,111,011 minus 5 plus 11,110,111 plus minus 9 11,110,010 minus 14. Discard carry. Overflow. Overflow occurs when number of bits in sum exceeds number of bits in addend or organd. Overflow is indicated by the wrong sign. Occurs only when both numbers are positive or both numbers are negative. 126 plus 11010 plus 58 __ 10,110,111 183. Sign incorrect, magnitude incorrect. Arithmetic operations with signed numbers. Subtraction of signed numbers. The parts of a subtraction function are: minuend, the first number; subtrahend, the second number; difference, the result. Subtraction is addition with the sign of the subtrahend changed. Arithmetic operations with signed numbers. Subtraction. The sign of a positive or negative binary number is changed by taking its 2's complement. To subtract two signed numbers, take the 2's complement of the subtrahend and add. Discard any final carry bit. Subtraction examples: find 8 minus 3. Find 12 minus 9. 0001008 plus 11,111,101 to 3 100001015. Discard carry. Minuend subtrahend difference. 000110012 plus 0001001 minus 9000100121. 11,100,111 minus 25 plus 11,101,101 to 19 11,010,100 minus 44. Discard carry. 10,001,000 minus 120 plus 0001110 minus 30 10,100,110 minus 90. Arithmetic operations with signed numbers. Multiplication of signed numbers. The parts of a multiplication function are: multiplicand, first number; multiplier, second number; product, result. Multiplication is equivalent to adding a number to itself a number of times equal to the multiplier. Arithmetic operations with signed numbers. There are two methods for multiplication. Direct addition. Add multiplicand multiple times equal to the multiplier. Can take a long time if multiplier is large. Partial products. Similar to longhand multiplication. The method of partial products is the most commonly used. Arithmetic operations with signed numbers. Multiplication of signed numbers. If the signs are the same, the product is positive. Plus x plus equals plus, or x equals plus. If the signs are different, the product is negative. Plus x equals, or x plus equals. Multiplication example. Both numbers must be in uncomplemented form. Multiply 3 by minus 5. Opposite signs, so product will be negative. 310 equals 0000112 minus 510 equals 111,110,112 2's complement of minus 5 0000101. oooooo11 multiplicand x oooooo101 multiplier oooooo11 first partial product plus oooooo second partial product oooooo11 sum of first and second plus oooooo11 third partial product oooooo1111 sum and final product. Final result is negative, so take 2's complement. 11,110,001 is the result, which in decimal is minus 15. Arithmetic operations with signed numbers. Division of signed numbers. The parts of a division operation are dividend, divisor, quotient. Division is equivalent to subtracting the divisor from the dividend a number of times equal to the quotient. Arithmetic operations with signed numbers. Division of signed numbers. If the signs are the same, the quotient is positive. Plus divided by plus equals plus, or divided by equals plus. If the signs are different, the quotient is negative. Plus divided by equals, or divided by plus equals. Division example: both numbers must be in uncomplemented form. Divide 0110010 by 0110010. Both numbers are positive, so quotient will be positive. Set the quotient to 0 initially. Quotient oooooo. 0110010 dividend plus 11,001,110 2's complement of divisor 10011010 first partial remainder. Add 1 to quotient oooooo plus 1 equals oooooo01. Subtract the divisor from the dividend by using 2's complement addition. 11,001,110, ignore the carry bit. 0011010 first partial remainder plus 11,001,110 2's complement of divisor 100000 remainder. Add 1 to quotient oooooo01 plus 1 equals oooooo10. Subtract the divisor from the first partial remainder using 2's complement addition. So final quotient is oooooo10 and final remainder is oooooo. Hexadecimal numbers. Hexadecimal numbers: decimal, binary, and hexadecimal numbers. 4 bits is enable. FF16 equals 25,510. Hexadecimal numbers: binary to hexadecimal conversion. Hexadecimal to decimal conversion. Decimal to hexadecimal conversion. Hexadecimal numbers: binary to hexadecimal conversion. Break the binary number into 4-bit groups. Replace each group with the hexadecimal equivalent. Convert 1,100,101,000,1,010,111 to hex. CA57 equals CA5716. Convert 10A416 to binary. 0001, 0000, 1010, 0100 equals 0010, 00101010. Hexadecimal numbers: hexadecimal to decimal conversion. Convert the hexadecimal to groups of 4-bit binary. Convert the binary to decimal. Hexadecimal numbers: decimal to hexadecimal conversion. Convert to binary by repeated division by 2 and then convert binary to hex. Repeated division by 16. Figure 2 getting the 2's complement of a hexadecimal number, method 1. Figure 2 getting the 2's complement of a hexadecimal number, method 2. Octal not users frequently convert binary to octal. Can group in 3 bits instead of 4 bits like hex. Symbols range from 0 to 7. Example. Convert 01011010 to octal. 132 equals 1328. Example. Convert 1058 to binary. 10101 equals 01000101. Binary coded decimal, BCD. Binary coded decimal, BCD. Decimal and BCD digits. Digital codes. Digital codes. Gray code. ASCII code. Gray code unweighted, no weights associated to the bit positions. Only one bit change from one code word to the other. Minimizes chance of error. Conversion binary to gray code example. Convert 10,110 to gray code. MSB of gray is set to the MSB of binary. Going from left to right, add each adjacent pair of binary code bits. Discard carries. Example. Convert 10,110 to gray code. MSB of binary number is 1, so set the MSB of the gray code to 1. 10110 binary. 1 gray code. Add adjacent pairs of binary numbers. 1 plus 0. 1. 1 plus 1. 0 plus 1. 1. 1 plus 0. 1. Conversion gray code to binary example. Convert 11,011 to binary. MSB of binary is set to the MSB of gray code. Going from left to right, add the binary bit to the next gray code bit. Discard carries. Example. Convert 11,011 to binary. MSB of gray code is 1, so set the MSB of the binary number to 1. 11011 gray code. 1 binary. Plus. 1. Plus. Figure 2.7 a simplified illustration of how the gray code solves the error problem in shaft position encoders. American Standard Code for Information Interchange, ASCII. ASCII code. First 32 are control characters. 128 characters. Uses 7 bits. ASCII code. Graphic symbols 20 hours, 3 FH. Digital codes. ASCII code. Graphic symbols 40 hours, 5 FH. Digital codes. ASCII code. Graphic symbols 60 hours, 7 FH. Digital codes extended ASCII code, 80 hours, FFH. Non-English alphabetic characters. Currency symbols. Greek letters. Math symbols. Drawing characters. Bar graphing characters. Shading characters. Error detection and correction codes. Error detection and correction codes. Parity error codes. Odd parity, odd sum of ones. Even parity, even sum of ones. The sum includes the parity bit. Parity bit can be at beginning or end of the code. Can detect single bit errors, but not 2 or more errors. Hamming error codes. Error detection and correction codes. Parity error codes.